Hi Internet, it's Dan again, and it's time to talk about some more audio DSP. Today we're going to talk about the Fourier Series, its applications as relate to additive synthesis and oscillators in general. The Fourier Series is a really fundamental technique to DSP in general, and it'll give us a good foundation that we can build a lot of new techniques off of in the future. We'll use the Fourier Series as an introduction to Fourier analysis in general, which is an area of signal processing that says that we can construct any possible signal using only a combination of sines and cosines at different amplitudes and frequencies. I'm not going to try and prove that idea here in this video, but I will provide references that explain this. After some discussion of the Fourier series, I'll use a demo to explain how some features in CRM and other synthesizers work. They use additive synthesis to create a lookup table oscillator and generate music that way. This will give us precise control of the waveform that we generate and allow us to keep from making aliasing that was happening in previous videos. Additive synthesis is a synthesizer technique that uses many different sinusoids, like sines and cosines, in order to create a lot of different sounds. These individual sinusoids can also be called partials and can be modulated in pitch and amplitude in order to create all kinds of interesting sounds. As opposed to the more popular subtractive synthesis, we can create different sounds by adding and subtracting partials instead of using filters. Now, filters are sometimes used in additive synthesizers, but aren't generally speaking part of the architecture of additive synthesis. Additive synthesis is in general not as popular as subtractive synthesis or frequency modulation synthesis or sampling or a range of other techniques, but it's still used in practice. Some examples of popular synthesizers that use additive synthesis are Image Line Harmor, Camel Audio Alchemy, and some features of X4 Records Serum. Additive synthesis is used most commonly in software plugins and is not frequently used in hardware, as it's rather expensive to implement these techniques in hardware. Let's jump into some discussion of the theory of the Fourier series. For our purposes, we'll use a definition of the Fourier series that says, any periodic signal can be represented as the sum of harmonically related sines and cosines. When we say any periodic signal, we mean any signal that repeats itself over a given period or over a given interval of time. Examples of these are standard waveforms in synthesizers like sawtooth, square, triangle, or anything else that repeats itself. When we say harmonically related, we mean that the sines and cosines that we're using are going to be integer multiples of each other. Meaning, if we want to generate a waveform with a fundamental frequency of 100 hertz, our harmonics will be 100 times 1, 100 hertz, 100 times 2, 200 hertz, 100 times 3, 300 hertz, 400 hertz, 500 hertz, 600, and so forth, up to infinity or as many partials as we want to use. It can be sort of difficult to grasp how using only sines and cosines can represent any possible periodic waveform, but there are some nice animations on Wikipedia that we can look for in order to get an intuition on this stuff. This animation shows us how we can break down a saw wave into a series of 4 different partials, or 4 different sine waves. If we look at only the first row here, we can see a function sine 2 theta over negative pi. What this means is we have a sine wave that is oscillating with respect to the angle theta, which is changing over time and causing this little line to move around the circle. We are taking the y position of the circle to be the sine, which is sort of where the definition of sine comes from. And the amplitude of this is scaled by 2 over minus pi, meaning the amplitude is around 2/3, and the negative sign meaning that the function is flipped over the y-axis. If you look at this part on the right, you can see that the sine wave sort of follows the path of our saw, shown in dotted lines that we're trying to approximate, but doesn't quite get there. It's sort of too wavy to really follow the sharp peaks of the saw wave. The Fourier series of the saw wave will tell us that at a sine of 2 times theta, or twice the frequency of our first partial, we need a signal with amplitude 2 over 2 pi, or 1 over pi. You can see that this has a lower amplitude because the circle is smaller than our first partial. We can visualize this by adding a circle with that radius to the end of our previous yellow circle. If you look at the waveform that results from summing the 2 circles and taking the y position at any point in time, you can see it's a little closer than our yellow line tracing the saw wave. Likewise, you can see with the blue and red circles that we have 3 times theta and 4 times theta as the frequency for our next sine waves, and we are decreasing the amplitude relative to our first partial. As we add more and more circles, or more and more sinusoids to our approximation of the saw wave, you can see that our tracing of the saw wave that we want is getting closer and closer. This is mostly true in general, that as you add more partials to your Fourier series approximation, you get much closer to the waveform you're trying to generate. We can see another example here with a square wave, where you can see one partial sort of loosely follows a square wave, and then at 3 times the frequency, or sine of 3 theta, scaled by some amplitude, we get a little bit closer to the square wave. Add in the harmonic at 5 times theta, and the harmonic at 7 times theta, and we start getting pretty close to the square wave, even though there's still some wiggling going on. Square waves form a special case of the Fourier series where we can reproduce the waveform using only odd-numbered harmonics. We don't have to use any even-numbered harmonics in order to reproduce our square wave. Now that we've sort of formed an intuition on how the Fourier series can approximate different waveforms, let's develop some equations that let us talk about this. As I said before, the Fourier series in general lets us use an arbitrary number of sines and cosines in order to represent a waveform. Let's begin our equation to formulate the Fourier series using only one cosine, just for simplicity though. This equation might look something like s sub 1 of x equals a sub 1 cosine of 2 pi 1 times x over p, where x tells us our point in time where we want to generate our waveform, and the value 1 means we are only using the fundamental frequency, or one partial if we're thinking in additive synthesis terms. The Fourier series says that we need to scale our cosine by some amplitude, which we will call a sub 1, multiply our position in time by the value 1, since it's the fundamental frequency, use 2 pi in order to indicate the periodicity of a cosine, and divide by p, which is our period. We want to be able to use a lot of different cosines in our Fourier series representation, so let's introduce one more cosine. Here we have s sub 2, meaning our signal using 2 sinusoids of x equals a sub 1 cosine, an argument, plus a sub 2 cosine, an argument. You'll see here that we have 2 times x, meaning we're at twice the frequency of our first cosine. We have the same terms of 2 pi and our period p, indicating the periodicity of cosine and our signal in general. We can extend this formulation to use an arbitrary number of cosines if we use plus ... plus a sub n cosine of 2 pi nx over p. We can state this and say that we can pick the value of n at any point in time to determine how many cosines we want to use in our formulation. The value of n will control how many partials we have in our Fourier series representation, and also increase the amount of high frequency content in our waveform. Our equation's starting to really have some power, but we have to keep in mind that the Fourier series also has to use sines as well. Let's extend our equation by adding n different sines using the coefficients b sub 1, b sub 2, all the way through b sub n. This will give us more flexibility in specifying different phases for our waveform's possible partials. The same properties about n here apply, that we are going to be adding more high frequency information as we increase our selected value of n. This equation is mostly correct for the Fourier series, but there is another notation that's used commonly in the signal processing literature, since it's kind of clunky to write out every time all of the cosines and all of the sines you want to use. We can use this notation to indicate that we are going to use the sum, or sigma, starting from small n equals 1, going up to capital N, of a sub small n cosine of 2 pi nx, and so forth, plus b sub n sine at frequency n times x. This means the same thing as the longer equation that we just had, but the notation is a little bit more compact. You can think of this notation as sort of like a for loop, where we add one more cosine and one more sine at the amplitudes a sub n and b sub n at the frequencies nx every time we go through the loop in our approximation of the signal. For completeness, if our waveform has a DC offset, or a zero frequency component, we have to include the coefficient a sub 0, meaning there is a zero frequency component that is necessary to represent our waveform. There are two special cases of the Fourier series for odd and even functions that will be useful for us as well. For odd functions, or functions that are symmetric if you rotate them around the origin, we can represent them using only sine terms, meaning we can set all of the cosine a sub n terms to 0. So we can use this shorter version of the Fourier series. Likewise, for functions that are even, meaning they're symmetric to a reflection over the y-axis, we can set all b terms in the Fourier series to 0, letting us use only cosine terms. So we can use this version of the Fourier series. Now that we've tackled some theory of the Fourier series, let's use this to create our own lookup table oscillators using these principles. Pulling up Octave, you can see that we have the same familiar framework here, converting MIDI notes to frequency, beats to samples, and so forth, where we generated melodies from the previous video using a lookup table. But here there's some new structure where we can generate our lookup table using a for loop in the Fourier series. Let's start by talking about some of the parameters. I have the BPM set to 80 beats per minute, sampling rate 48 kilohertz, the amplitude of the melody 0.2. I've set our lookup table length to be 2 to the 11th. I've selected 35 partials and a melody of ascending perfect fourths. I've selected this melody so that we can hear the differences in quality of lower notes versus higher notes, which is going to change dramatically as we shift the number of partials. Let's initialize our melody array to be empty and use our same MIDI to frequency and beats to samples functions that we've used in the past. And in this loop, we will generate our lookup table using the Fourier series. Let's generate a saw wave here. So let's initially set our lookup table to be all zeros for the length of the lookup table, loop through the partial index, starting from 1 to the number of partials. And for each time through the loop, add to our lookup table -2 over the partial index times pi times -1 to the power of this partial index times our sinusoid at 2 pi times the partial index times our linearly spaced points in time. This will generate a saw wave approximation with the length, LUT length, with the number of partials that we've set in num partials. This equation comes from this formulation of the Fourier series, where you can see our B coefficients are the expression -2a, or the amplitude, over pi n times -1 to the n. This is a special case for saw waves, and the Fourier series for many functions are a little bit more complex than this. I won't go into detail on how to derive these coefficients, but just know that it is possible to derive them for any possible periodic signal. In fact, if you're comfortable with calculus, it's really not that complicated in order to generate these, but I won't get into it today. After we've generated our saw wave approximation in the lookup table, we can create our inline function in order to index this periodically, as we've talked about before. We can loop through all of the notes in the melody, get their frequency, and I have their length all hard-coded to 0.5 quarter notes or 1/8 note. Set this tone to be our amplitude times get sample from the lookup table, append to the melody, and write to the file, Fourier series saw arpeggio. Let's run this, change directory, pull it up in Finder. Well, that was interesting. The beginning of this seemed a little bit dull, as if it wasn't a pure saw wave. The middle of it sounded pretty good, but then the end of it had some aliasing going on. Let's listen to it again. Notice the inharmonic section at the end where you can hear that there are sort of some parts that sound metallic, or not like a saw wave at all, and kind of like digital artifacts. We can get a closer look at what's happening in this using Sonic Visualizer, an application that's really handy for visualizing all kinds of audio information. It's a free application and I definitely recommend checking it out. On this view, a spectrogram of our generated file, we can see time on the x-axis, frequency on the y-axis, going up to a possible 24 kilohertz, which is the Nyquist frequency for our sampling rate 48 kilohertz, or the highest possible tone that we could possibly represent, and increasing color from black to green to red, showing stronger frequencies at each point in time. If you look at the beginning of this file, you can see that only up to about 1.6 kilohertz are shown on the y-axis. As our notes increase in frequency, we're using more and more of the frequency bandwidth till we reach most of our possible bandwidth. And what were once evenly spaced notes become sort of all discombobulated and thrown all around the frequency spectrum. This sort of disorganization of each of the tones is what we hear as aliasing. Now what we see here can be explained really cleanly using our Fourier series representation. In octave, we set our script to use 35 partials, which means that every note there will be a fundamental frequency plus 34 additional sine waves that occur at integer multiple frequencies of the fundamental frequency. For example, if we look at this note with a fundamental of around 500 hertz, we can see that the first harmonic is around 1000, then around 1.5K, and then around 2K, and then around 2.5K, so on and so forth, up to around 16K. Now what happens when these partials go over our Nyquist rate is that they start becoming lower frequency. That's what you see here when we have some different bands that start getting closer together. We have partials that are so high in frequency that they can't be represented at 48 kilohertz anymore. We hear these as audible artifacts. As our notes increase and we have more and more high frequency components that can't be represented at stronger and stronger amplitudes, we hear more aliasing. Let's listen to this file one more time with an ear towards that. Using this conceptual framework, we can see that this note in the middle sort of has the most saw-like characteristics, as there's no aliasing, but there's still lots of harmonics that we use to perceive as sort of saw characteristics. If we added more partials, we could sort of increase our quality of the representation for the lower frequency notes at the expense of having more aliasing at high notes. If we decrease the number of partials, we can reduce the amount of aliasing, but reduce the number of partials that create the saw-like sounds at lower frequencies. As an example, let's change our script to only use 2 partials in our saw wave. Run it again, open in Sonic Visualizer, and you can see now that there are only 2 partials that happen at any point in time. Let's listen. This new version doesn't really sound like a saw wave at all for the initial part, as we're missing most of the harmonics that we used to identify as a saw wave. But on this last note, actually, you would be hard-pressed to separate this from an actual saw wave, since it has all of the perceptible harmonics. In this sense, higher frequency saw waves become less and less distinguishable from a pure sine wave. Let's do one more quick example in octave where we generate the Fourier series for a square wave. We can use this Fourier series representation of our square wave that tells us that we only need the A coefficients, or only the cosine parts, and we also only need the odd values. We can see this because our A coefficients are 0 if n is even and n is not equal to 0. Our cosine coefficients for the odd harmonics are going to be 2 times the amplitude over n pi times the quantity -1 to the power n minus 1 over 2. Again, this is an interesting special case for square waves, and actual Fourier series for other less ideal functions are likely not to be this neat. If we pull up a similar script in octave that has all of the same parameters with our 35 partials, change out our generation of the lookup table for this new function, we can run this and listen to it. And you can hear again, like our saw wave with 35 partials, that in the beginning it sounds a little bit too dull to be a square wave, in the middle it sounds just about right, and at the end there are too many high frequency partials. To wrap up this video, this serves as a good introduction to the world of Fourier analysis. Again, as mentioned before, we can create the Fourier series for any periodic waveform using some techniques from calculus, and we can represent that waveform with increasing resolution and increasing accuracy by using more partials. And we can extend these techniques in the future to the discrete Fourier transform, which says that we can represent any finite duration sequence, even if it's not periodic, as long as it doesn't last for an infinite amount of time using a set number of sines and cosines. This is a very important tool in signal processing, just like the Fourier series, and can be used to develop all kinds of frequency analysis tools. We've used this Fourier series in order to create a more practical lookup table approximation where we can control the amount of resolution for each waveform as well as the amount of aliasing that we get. We could also create arbitrary waveforms by picking different Fourier series coefficients. Some references that were helpful to me in putting this video together that might help you are the Fourier series Wikipedia page, which has some very nice animations, as well as sort of an overview of the technical formulations, as well as some historical notes. A video lecture from Rich Radke at Rensselaer, I think that's how you say that, Polytechnic Institute, that talks about the Fourier series and sort of more theoretical details than I gave today. Sal Khan has a great introduction to the Fourier series with Khan Academy. Highly recommend this if you want sort of some nice pretty colors in order to talk about the Fourier series. A video from Synth School that has some nice audio demos on the Fourier series and additive synthesis, as well as some notes from Swarthmore that have some nice cases of the Fourier series and talk sort of more about the theory. Thanks for watching this video. I hope you got something out of it and learned a little bit about the Fourier series. This can be a very practical technique for DSP in generating lookup tables and different forms of synthesis in general. And I hope you can use it in your creations in order to create all kinds of different waveforms and sounds. Leave any comments if you have anything you want to respond to or any questions that you have for me. Like and subscribe this video if you enjoyed it. Share it with your friends. Other than that, I'll see you next time. Thanks for watching.